First thing, this number in scientific notation, the value C, must always be a number that is between, where C is greater or equal to 1 and less or equal to 10. Kashan, knock it off. If we are looking in standard notation today, I'll give you this on your homework, and I'll ask you to write it in scientific notation. In scientific notation, we should be moving the decimal between the 2 and the 8. In product form, we write it as 2.89 times 100,000. But on the quiz today, you are simply going to be asked to write it in scientific notation. So, if we are writing this, you're putting this up here. Not down there. 2.89 times 100,000 would still be 2.89, but now we're going to write it times 10 to the 5th power. And as you look at this, we are moving between, we want our decimal here, we move back, and we're counting how many places. This number will always be positive if the number in standard form, please write this down, if the number in standard form is greater than 1. Anytime it's greater than 1, I will always have a positive exponent. So when I look at this one, it's 8 times 0.001. And as I am writing it in standard form, that's going to be 0 point, as we are looking at that, 0.008. Which means if I want the decimal to be behind the 8, I'm going to be moving it. And in this case, in scientific notation, I'm going to have 8 times 10 to the negative 3. I'm going to have a negative 3. This number will always be negative if in standard form, anytime I look at that standard form, so standard form is way over here. So if I look at standard form, if it is a number that is between 0 and 1, a decimal, between 0 and 1, this will always be negative. So when it's a number that is less than 1, usually between 0 and 1, in standard form, this will always be a negative exponent. So as we look at this next part, we're going to look at a few videos. And it asks you in your notes. We're going to look at this one where we're zooming in and out. I have this attached to the daily planner. We're going to look at the blood cells, which is looking at really small numbers. And then we're going to look at this one with vast distances, which is kind of looking at really large numbers. So the first one looks like this. And try to look at why you want scientific notation.
We're on a tour of New York City with math as our companion. This town is a study in contrasts. Central Park feels so natural and peaceful, but a quick cab ride downtown showcases mesmerizing architectural feats. We can use scientific notation to help us understand such a wide range of places and a very wide range of distances. Look at a familiar number, 200. In scientific notation, it's 2 times 10 squared. Scientific notation is expressed in 2 parts. The first part is a number greater than or equal to 1, but less than 10. The second part is a power of 10, which the first number is multiplied by. New York City might seem like a big place, but when you consider a perspective that's out of this world, you see it's quite tiny. Let's look at Manhattan Island's length in comparison to the distance between the Earth and the Sun. Manhattan Island is 13.4 miles long, and the average distance between the Sun and the Earth is 92,900,000 miles. That's a lot of zeros to keep track of. There's another way to describe this number that's often more useful. Here comes scientific notation to the rescue. We can write the vast Sun-Earth distance as 9.29 times 10 to the 7th miles. Count how many places you have to move the decimal point to get to a number between 1 and 10. That's the power of 10.
It's counting places.
Scientific notation is a condensed way to write some numbers, and it also provides an easier way to compare them. Watch. How many Manhattan lengths would it take to reach the sun? We need to divide the distance to the sun by the length of Manhattan. In scientific notation, that can be written as
This is the type of problem we'll see towards the end of the unit that'll be on the test.
break that into parts, since it's multiplying and dividing. It's the same as 9.29 divided by 1.34, all times 10 to the 7th divided by 10 to the 1st. 9.29 divided by 1.34 is 6.93 to the nearest hundred. Then, 10 to the 7th divided by 10 is the same as 10 used 7 times in multiplication, divided by 10. Canceling out one of the 10s, you get 10 used 6 times to multiply, or 10 to the 6th. The ratio is 6.93 times 10 to the 6th, or 6.93 million. Using scientific notation to divide is often simpler than doing the long division in expanded notation. This goes for multiplication too. So how far is it to the sun? To find out, travel the length of Manhattan 6.93 million times. At 60 miles per hour non-stop. That would take more than 176 years.
So when we are looking at, that was our vast distance. When you look at this one with blood cells, they're showing us a way that scientific notation is used with really small numbers.
The human body has fascinated ancient and modern scientists alike. Even though it's one large mass, our body's host to a multitude of microscopic cells. You hop on the doctor's scale to determine your overall body mass. But how do you express the mass of things too tiny to register on that scale? One way is with scientific notation. We can use scientific notation to represent virtually any rational number, and it can help us compare very large or very small things. Scientific notation is a way of writing any number as a number greater or equal to 1 and less than 10, multiplied by a power of 10. So you can use it to express the weight or mass of your whole body in pounds or kilograms, or ounces, tons, milligrams, or micrograms. Or you can use it to express the mass of teeny tiny cells and parts of cells that make up your body. Powers of 10 are used in scientific notation. The exponent on the 10 tells us how many times the base number is used in a multiplication. Let's go inside the human body. The average adult has about 5 liters of blood, or roughly 5,000 grams. Meanwhile, a single red blood cell's mass is about this number of grams. We can write these numbers in scientific notation. The exponent of 3 means we multiply 10 times itself 3 times, which is 1,000. But what's the negative exponent? That means it's 1 divided by the base to that power. So 10 to the minus 11th power is 1 divided by 10 to the 11th power. So this is a very low number, close to 0, but not as near as 10 to the negative 20. But 10 to the negative 20th power is even lower, nearer to 0, than 10 to the negative 11th power.
So when you think of that, is 10 to the negative 20th, is it going to be negative? Is 10 to the negative 20th going to be negative? No, it's still going to be a positive number, right? Here they're looking at the views of the Milky Way, it says, looking at the Earth, and you're going to see this change. They go all the way from really far out, 1,000 light years away, to the positive 20th, all the way down to the negative 20th power. So as you're looking at how the solar system, they're kind of telling you this is how far out, and down here. So looking at these two, as we look at the orbit of the moon, the Earth, we're 10,000 kilometers, 100, down to 10. Okay? And when you think in science, last year when you were studying leaves, you were looking at the cells, right? Individual leaf cells, the nucleus. We're now looking at the DNA of that. So getting smaller and smaller. So here's the powers, right? Still getting smaller, right? So we're looking at the single proton. So when you are looking at this, so it says you can view it from the Milky Way, which is 10 million light years away, and we're going to move all the way down, in this case, to DNA, subatomic universe, electrons, protons. And I attach this to the daily planner, and it says you can set it manually or autoplay. You can tell it how fast to move, so if we want to have it move faster. You can see how quickly, if we are looking at the times 10 to a power, things are going. And I just want you to be aware that this is out there for you to take a look at. If you're trying to understand scientific notation and the powers of 10, this kind of gives you a good visual of what those powers of 10 mean or what they look like. So the key thing that we want to look at, anytime we're looking at scientific notation, why do we use it? We're pretty much using it for this one purpose, to represent really large and really small numbers. So very large and very small numbers. In that, whenever we have a large number, that's when we're going to have our number from 1 to 10 times 10, and it's always going to be a positive power, right, if it's a large number. When it's a really small number, we're not talking negative, we're talking decimals, really small, really close to 0. That's when that first number of a number between 1 and 10 times 10, and this is when you will have a negative exponent, right? And always looking at the negative or positive exponent is how far you're moving things. That's really why we're using it, okay? And it's how far we're moving. So today we practice a little more with scientific notation. Yep.
Go back.
Yeah, you can go back.
Can you what?
Go back.
Can those satellites actually zoom in that far?
Well, it's not like a satellite, but then it's a telescope, like a microscopic telescope that's getting, so like if you were in a research facility and you're doing cancer research and that kind of stuff, right? You want to break things down and look at the really tiny stuff, okay? All right, so then we want to take a look, and again, this will be attached on the daily planner, so if you didn't get it down or your shoulder card didn't, you can go there. So we're now looking at this part on the top of that next page where it says 0.005. Lightning, it says, consists of 3 or 4 strikes. The time between each strike is this amount of seconds, 0.0005 seconds. We're going to write it in scientific notation. That means the first number must be between 1 and 10, which means it has to be 5. We're going to move our decimal point over. If we are counting, how far are we counting going from this place value to over here? We should be counting 5 places. But since it's a small number, I'm not going to have positive 5, but negative 5. So the exponent is going to be negative 5. We did move our decimal 5 places. And in scientific notation, my final answer would be 5 times 10 to the negative 5. So there'll be a few questions in your homework where I'll ask you, simply write it in scientific notation or write it in standard form. So this next one, again, it's in standard form, but it's a really large number. When you do it on the quiz, I had some people go, oh, can I just put 9.6? You have to go all the numbers until you get to the 0. So we should have 9.681. You need to have all of the numbers until you come to the zeros. And again, we're not counting 5 zeros. We're counting how many places are we moving our zeros. So 3, 6, and in this case, we should have 8. It's a positive 8. The reason it's positive is our number was larger than 1. So if we are looking at the maximum distance from Earth to Jupiter is that many kilometers, we are going to write it in scientific notation as 9.681. 681 times 10 to the 8. So as you take a look at the top of the next page, you are asked to write them in both standard form and scientific notation. And if you don't have a calculator, this next page is going to ask you to grab a calculator to look at it on the calculator. So, if we are taking a look at 1, 2, and 3, please tell your shoulder partner in 1, 2, and 3 which ones will have a positive exponent. Tell your shoulder partner right now. Which ones have a positive? In our first one, Zach. From back here, where the decimal is, even though there isn't a decimal, to move it to behind the 9, times 10 to the
1,000.
Okay, how many place value? I just need to know times 10 to a power. How many places did you move it? 3. So I'm going to have times 10 to the 3. Okay. Timothy in the next one, 3.25. So to move it over here, 3.25 times 10 to the negative 4. If we are looking. So we had to move it 1, 2, 3, 4 places to get it. Okay? It's a 3. If I'm looking at the next one, Nolan, 1.207 times 10 to the, how far? What'd you say? I didn't hear you, Nolan. How? Did you say 7 at first? So 3, 6, 7, 8, 9. So it should be times 10 to the 9. Okay? So as you were looking at those answers, 9 times 10 to the third, 3.25 times 10 to the negative 4, 1.207. That's what you're going to be asked to do on your homework quiz today. Write a number from standard to scientific. If I was looking at the numbers down here, please try writing them right now on your own in standard form. 8,200. Put 2 zeros behind it. Nope, it wanted to tell us to move it 2 places. It should be 820. It is not telling us the number of zeros, it's telling us to move it 2 places. Okay? Next one, if I am looking at Janessa.
It'd be 55 million.
How many zeros do you want behind that 551? 8 zeros. And so sometimes I will even write it out like this. And then because it gets to be so many and I'm writing them 1, 2, 3, 4, 5. And it gets to be a really large number that even reading the numbers sometimes we make mistakes. So by putting that I have 8 zeros there, that I'm kind of sure that I have that. It's not 10 zeros, it's moving it 10 places to the right. Okay? So the last one, if I am looking at that, Addie, what should I have? 0 points. I'm going to have 6 zeros behind the decimal point. 298. So when I'm looking at this again, this is 6 zeros behind that decimal point. It's a total of 7 zeros altogether if I count the place value that I was looking at. Okay? So, right now what I need you to do on your calculator, if you don't have a calculator, grab one. You're going to put in the number 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9, 8, 7, 6, 5, 4, 3, 2, 1. That's exactly what it says in your notes. Put in 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9, 8, 7, 6, 5, 4, 3, 2, 1 and hit equal. And mine comes out to be 1.219 if I was estimating it. 10 to the 17. Okay, these are different ways that it might look on your calculator or in a spreadsheet. Sometimes it just has the exponent up here. Other times it has times 10 to the 17, so it just depends. So if you're in a science class or if you're in here and you get a weird answer with that E17, that doesn't mean E17. This means this answer is 1.219 times 10 to the 17th power. Now usually we don't put all of those numbers that come out behind it, 1.289, 326, we don't put all of that down because we're going to estimate it. It's a huge number, right? If I was going to write this out in standard form, this would be a 1219, and it would be followed by, this is 3 places, it would be followed by 14 zeros, right? That's a huge number. Even to say the number, like to come up with a name for that we have a name, but it's really a big number, right? Please, on your calculator now, take 0 point and put 1, 2, 3, 4, 5, 6 zeros here, and then 1, 2. And then put in your calculator times another really small number with 6 zeros, 9, 8, and multiply those two and see if you get 1.176 negative 13, right? So these are all the different ways that it might look on your calculator, okay? Okay? You want to make sure you understand that if you were looking at this on your calculator and you put down this for an answer to Sean and Elijah, I would mark it wrong, right? This is not the answer. 1.176 negative 13, this is not raised to the negative 13. You need to know that this is 10 to the negative 13, which would mean in standard form, right? If I wanted to write it out in standard form would be 0 point, and here I would have 12 zeros, and then I would have 1176. But I would have 12 zeros before that, okay? So you just want to make sure you're understanding how to look at really small numbers. You are going to start right now on C8. And when you start on C8, you have to write this number that's given in number 1 in scientific. If they give it to you in standard, you must write it in scientific. Then you're going to rank them from the smallest to the largest. As you are